Welcome. Now I'm going to start the fast reducing reagents, that is lithium aluminum hydrates. Lithium aluminum hydrate. So we know very well about of this lithium aluminum hydrate. It is a strong reducing agent. A strong reducing agent. So first we look at how its structure is and why it is a strong reducing agent, and we will do that while you doing any reactions with lithium aluminum hydrate, what type of solvents we will take and how we will handle this lithium aluminum hydrate, because it is a strong reducing agent. So this all these things we will discuss, and also we will discuss that where it will do the reactions and which case it will not react it. So that all the details we will discuss today. Okay, so first we will look at how its structure is. This lithium aluminum hydrates, this LiAlH4 plus, and this is another is LiAlH4 minus. This is the structure of this lithium aluminum hydrates, and it is this lithium here. Let's say one hydrogens, and this hydrogen plane, and one is above and one is in the back. This is the structures of lithium aluminum hydrates, and we see that in this boron families, this aluminum are the boron family. So these are generally the electron deficient groups. These are electron deficient groups. Okay, so this boron family are electron deficient groups. The reason is that this borons, if you see that this atomic number is 5, that is equal to 5. So this is 1s2, 2s2, 2p1. So this valence electron is 2s2, 2p1. Similarly for aluminiums, this is 3s2, 3p1. The valence electron is 3s2, 3p1. So for this case, if you say for boron case, then what we see that this boron and 3 valence electrons, so one is here, another is here. Okay, so if it is coordinately if it is sharing this electron with, let's say, one hydrogen and one hydrogen, still its octet is not completed. How many electrons are there? 1 2 3 4 5 6. So still this is electron deficient groups, because octet is not completed. Whenever octet completed, then only that compound is stable. For this 2 electron is needed to complete the octet. So this is a electron deficient groups. Similar case, this aluminum also on that groups. This has the 3s2 3p1. So here also 3 electrons are there. If it is shared with hydrogen, 3 hydrogens, then also its octet is not completed. Okay, so 2 electrons remain to complete its octet. But now when we have that aluminum LiAlH4 minus or BH4 minus, on that case what will happen, that if we give that one hydrogen atoms, let's say if that, and then on that case what will happen, that here hydrogens, and here hydrogens, and whenever one hydrogens will coordinately bond with this, then here we get that although octet is completed, 8 electron, 1 2 3 4 5 6 7 8, but this get the negative charge. It means that whenever a electron deficient groups get a negative charge, it become a very highly reactive, means it become a electron rich groups. So this always wants to react with other electron deficient groups. Okay, so that's why you see that this LiAlH4 minus will give that H minus, and this will like a nucleophile, and this will react to any electrophile or electron deficient groups. Okay, so now the question is that why it is a strong reducing agent. So strong reducing agents because you will see that this is the electron deficient groups, and whenever it one hydrogen atoms, when if make a coordinate bond with this, then it is getting a negative charge, and electron deficient groups having a negative charge, it means that this is a highly reactive groups, because this is electron deficient groups get negatively charged after coordinately bonded with hydrogen atoms, so it become electron rich and highly reactive. This is the one reasons why this is highly reactive and strong reducing agents. And second reason is this aluminum hydrogen, here this H, here this H, and here this H, and here this H. So what we say that here we are getting that H minus. Okay, so now that this hydrogen here, this that valence electron is 1s orbitals, and for this aluminum that valence electrons are orbitals are 3s and 3p. So if 3s and 3p, the bond is very weak, because the one is like one is this and other is like this. So the bond formations between them is very weak. So that's why this aluminum and hydrogen bond is unstable and weak. So it will highly reactive, so it can easily give this hydrogens. Okay, so it easily donate hydrogen atoms. But for the case of, if we say that for case of NaBH4, here that BH4 minus, on this case this boron, here this hydrogen, here this hydrogen, here hydrogen, here hydrogens. On this case this boron has 2s and 2p orbitals, and this is 1s orbitals. For this case bond is comparable. BH bond is comparable because this is 2s 2p and 1s orbital coupling. Okay, so this bond is comparable, so this is less reactive than LiAlH4. Okay, so this is the two regions that makes that lithium aluminum hydrates a strong reducing agents. First reason is that this is a boron family, the electron deficient groups are directly getting a negative charge, and so that it's become a highly reactive. And second case, that this aluminum and hydrogen bond is a very weak due to a very size difference. So that's the regions it easily donates the electrons, and it is a highly reactive. Okay, this is the two regions that makes that lithium aluminum hydrate a strong reducing agents. Now we look that, so this lithium aluminum hydrates, when we react with water, because water is available in the surrounding in the atmosphere, so what will happen, this lithium aluminum hydrates, when it will react with the water. So every case we will look that reagent whether it is reactive with water or not, whether it is reactive with air or not. Air means that water is there. So first we will look that whether that reagent is reactive with water or not. If that is reacted, then we have to take that reagent in a that conditions, that is let's say anhydrous conditions where water is absent. So lithium aluminum hydrate is reactive with water. So this lithium aluminum hydrate is reactive with water, and while this lithium aluminum hydrate is reactive with water, it produces hydrogen gas. So always be careful that whenever you are taking lithium aluminum hydrate, so we should take in a anhydrate conditions. So it is taken in hydrous conditions, okay, like you have taken in a dry ethers. Okay, so whenever you're taking the lithium aluminum hydrates, so because if it is in contact with the moisture, in contact with the air, then it will be reacted with this water, and it will produce a hydrogen gas. Okay, so whenever you are taking lithium aluminum hydrate, always take in a anhydrous condition. Anhydrous condition means no water is present, no water. On that conditions only you will take this lithium aluminum hydrates. So this is about of the reactive of lithium aluminum hydrate with water. Now what type of solvents you will take whenever you are taking this lithium aluminum hydrates? Solvent used. So since this is a reactive with water, so water is like a polar molecules. Okay, so these polar solvents you will not take whenever you are taking the lithium aluminum hydrates. Okay, so solvent is always taken that non-protic solvents. Non-protic solvents is taken, and always not that polar solvents is not taken whenever you are taking the lithium aluminum hydrate, because it react with that solvents itself and it will not all that lithium aluminum hydrate is react with these solvents, and it no reagent has left to do where we are supposed to do the reactions. So the solvent always has to take that non-polar protic solvents like you will take that diethyl ether, or you can take that THF. Okay, so note that diethyl ether is more soluble to lithium aluminum hydrates. Okay, and this is less soluble. Reason is that, see here, this type of molecules is there. So here that since here rigid structure is there, so this is less soluble to this lithium aluminum hydrate, where diethyl ether is more soluble to lithium aluminum hydrate. But still, whenever you doing the reactions, we generally take THF as the solvents than the diethyl ethers. The reason is that this lithium aluminum hydrate is not exist in a pure form. It means some catalytic impurities are there. So for that reasons, diethyl ethers is not a good to take as a solvents whenever you are taking lithium aluminum hydrates, although it is a more soluble. Okay, for the case of THF, there is no such cases. If that lithium aluminum hydrate is not there, then also this THF will be a more convenient to use. So maximum times we will see that THF as a solvents whenever you are taking that lithium aluminum hydrates. Now after doing that reactions with lithium aluminum hydrate, how we will do this workup? Okay, another thing is workup process, means after completion of the reactions. So after completion of the reactions, then if all the reactions whatever that lithium aluminum hydrate you used that already reacted with that reactants, then only we will add the water. Means workup how will you do? So generally wherever you do the reactions with lithium aluminum hydrate, that beaker is hot. Okay, so for that case we will take generally in a ice bath. Keep that beaker in ice bath, the reaction mixture present in a beaker, that we will take in a ice bath, and we will add slowly a ethyl acetate, means that reaction mixture is quenched by a ethyl acetate, and we will add slowly that methanols followed by a cold water, because now we are adding cold water after completion of the reaction. This workup means after completion of the reactions we will add the water, cold water. First we will take in a ice bath, and we will add that, we will quench this reaction mixture by ethyl acetate, and then we will add methanols, and after that we will add a cold water, then we will do the filtrations. Okay, so this is how we will handle that lithium aluminum hydrate while doing the reactions. So this is all about of that experiment. Okay, so why I'm talking about of this experiment is, see, whenever we do the reactions in organic cases, the experimental result is the ultimate. After doing the experiment, whatever you get the product, according to the product we will make a mechanism. So this mechanism comes the second case. First case is that whatever we get the product, what is the experimental results. From that experimental results, whatever you get, accordingly we will make a reaction mixture. Okay, so this theoretical will comes after the experimental. So whenever you get in the reactions mechanisms, that reaction mechanism for different cases, maybe sometimes concept is not used, that will used, that reaction mixture that reaction mechanism is derived according to the product, what type of product we get, the accordingly we will make a reactions mechanisms, what should be a reaction mechanism, how it may be occur. Okay, so that's the reasons that experimental result is very very important. Okay, so whenever you are doing the reaction mixture, sometimes you have to memorize the reactions mechanism, because these reactions mechanisms will be differ for different, because this reaction mixture is derived after we are getting the experimental results. Okay, so now we will look that how exam point of view, how this lithium aluminum hydride, this reagents, where it will be used and where it will not used. So this lithium aluminum hydrides, so these reagents generally where we used is that it is used where this is, here we see that this here H minus is coming. Okay, so this is a nucleophile. So this lithium aluminum hydride is used, is generally prepared or more efficiently used to a polar multiple bonds. So it is efficiently used to polar multiple bonds. Like if we have this CO carbonyl groups, okay, this type of groups, it is more efficiently used. Why? Because here that electron difference is there, electronegativity difference is there. Let's say here delta plus, here delta minus, then this nucleophile will attack to this electron deficient carbon centers. Okay, or it is also used, it is used to reduce polar bonds. Okay, it is efficiently used to reduce polar multiple bonds, or it is used to reduce polar bonds. In this case we will see that maximum times this lithium aluminum hydride is used, either it may be a polar multiple bonds or it is a polar bonds. In this case we will use the lithium aluminum hydrides. And the next case is it is not used, not it is generally not efficient to reduce non-polar bonds. Non-polar bonds, like you have that C double bond or C, or you have that C triple bond or C, this type of case that lithium aluminum hydride is not used, because here there is a no electron difference, means here that no electrophilic center. So if electrophilic node center is not there, then where this nucleophile will be attacked. Okay, so this is that where lithium aluminum hydride is used, that need that polar multiple bonds, and or it may be a polar bonds. On that case we will use the lithium aluminum hydrides. But if it is a polar non-polar bonds, on that case this lithium aluminum hydride is not used generally. Exceptional is there. Exceptional case is let's say if that this non-polar bonds, if it is as adjacent to it any alcohol or amine is present, on that case it will be lithium aluminum hydride can be used to reduce. Okay, that we will discuss while we are discussing more about it. Okay, so first we will look now is that the mechanism, how it is. After that we will take example wise all these cases. Okay, so first we will look that how that mechanisms of this lithium aluminum hydride. Let's say we have this type of carbonyl groups and you are doing that lithium aluminum hydride. let's say you have this one equivalence and this is one equivalence, or simply I'm writing, let's say this is one and this is one. Okay, I'm doing these reactions. How will do that? So what happened, this solvent is THF is taken. Okay, so now what we'll do, that this lithium aluminum hydride, this is in the form of Li plus and LiAlH4 minus, this is exist in this form. Okay, so what will happen, that here this is a lone pair is there, so this lone pair and this lithium, okay, this is set to coordinately bond with this lithium, so this will be like this. Oh, and this lone pair is coordinately bond with this lithium plus, and this is getting partially a positive charge. So this, if electronegativity groups getting a partially positive charge, means it obviously abstract electrons from this carbon center, means here you get that delta positive charge. Okay, so now whenever you're getting a delta positive charge, so this is in this condition, this is L, H, H, H and H. So I says that whenever this aluminum make a 4 bonds, it is octet, although its octet is completed, but it is a electron rich groups and it is highly reactive, because this bond is also a weak and unstables, and also this is going to be electron rich group, so this will attack to this groups. Okay, and this will this delta positive charge made on oxygen get removed by shifting this double bonds to here. Now what will happen, now this is going to be like this, here one hydrogen will come, this hydrogens, and this is going to be O minus, this is going to be O minus, and here we have that lithium plus. Okay, and this will be one hydrogens already gone here, so this is aluminum, and one hydrogen has gone, so 3 hydrogen has left. Okay, again it become a electron deficient groups, because it become a 3 bonds and octet is incompleted, so this is again a electron deficient groups. So this is fulfilled by that solvents we have taken, that THF. So THF is in this form. Okay, so here lone pair is there, so this lone pair will be make coordinate bond with this aluminum, this is making a coordinate bond with this aluminums. Okay, so now for this region, this aluminum is soluble with this solvent THF, because they are coordinately bond with this aluminum and this solvents, so this pool is a soluble. Okay, so this aluminum is soluble with this THF. Now what will happen, here we see that this aluminum, here it will coordinately bond with this THF, but here again that oxygen has the negative charge, so this is a negative charge, here is a lone pair, so electron rich is more in the case of negative charge than the lone pair. So what happened, that this negative charge attack to this aluminums and this coordinate bond is removed. Okay, because this negative charge, here electron density is high compared to this lone pair, where whatever this aluminum, here this is the electron deficient groups. Okay, it need electrons, but from this negative charge it get more electrons rather than this lone pair, so it prepared to get this negative charge electrons, because this is having a high electron density compared to this, so this will comes to here and this is removed, so this becomes this hydrogens, here oxygen is there, and this is get to aluminum. Okay, and here we have that 3 hydrogens is there, because 1 hydrogens already you have used here. Okay, so now what will happen, let's see that here this aluminums again it get the 4 bonds, so if it get 4 bonds, it get again the negative charge. If it is negative charge, then this hydrogen is reactive, so it can easily give H minus, so again another equivalent of this carbonyl groups we will take, and what will happen, that now this Li plus again is in the solvents, because it after it react, this lithium plus comes to the solvents. Okay, so this lithium plus again may coordinate bond with this oxygens. Again here that the same case as it is made here, again it will make a delta positive charge, so the abstract electrons. So here delta positive charge, again this hydrogens attack to here, and this is removed this delta positive charge, so it again going to becomes like this hydrogens, and here O minus, and it is going to be here is Li plus, and is again going to be like this aluminiums, and one side this oxygen, and other side see that two hydrogens already removed, this hydrogens already comes to here, so now left two hydrogens, so two hydrogens are there. Okay, so this is again get a 3 bonds. If it is a 3 bonds, again it become a electron deficient groups, and this electron deficient is fulfilled by a solvents, so solvents again come. Again the solvents will come, and again it will make coordinate bond with this, but now again whenever it created, so again here is a negative charge, so this negative charge again attack to here, and again it removed, so again it will be repeat the same way, that is going to be that this aluminiums, here one oxygen, hydrogens. Okay, so now this is attacked, so this is also comes oxygen, hydrogens. Okay, so two hydrogen has left, so I will make that two hydrogens. Okay, now again it get a 4 bonds, again it get a negative charge, so again this hydrogen get reacted, so again another carbonyl groups is there, another carbonyl groups, because in the solvents we will take that the maximum amount of carbonyl group so that it will react, so again this will be there, again this lithium plus will come and coordinately bond with this, so again here delta positive charge has created, again this will attack here. Okay, so again it will become like this O minus, and it become H, and it will become Li plus, and this will become negatives, and again this one has removed, so again 3 bonds will be there, that is aluminiums, H, and 1H, because 1H already taken here. Okay, this H already used here, so again that 1H is there, again this is a 3 bonds, again it become electron deficient groups, again it is fulfilled by a solvents, so this is again going to react here. Now see here again you have negative charge, so again it will react attacked here, and this is going to be like this. So now what you see here, this is going to be this aluminiums, here we have these groups, and again one hydrogen is there, again it become a negative charge, because again it make a 4 bonds, again it is a reactive, so another carbonyl groups will be there, and again this is make a coordinate bond with lithium plus, and this is delta positive charge has created, so again it will attack to this, so again it will become that this H comes to here, again this is become O minus and Li plus, and plus this is there, again this went, so 3 bonds are there only. Okay, so 3 bonds, again this is getting a electron deficient groups, and it is fulfilled by solvents. Okay, now this is negative charge, again it will attack to this, and is again removed, so now what will become it is aluminiums, here one, hydrogens, oxygens, hydrogens, hydrogens. Okay, again it getting the negative charge, so in this way that all the hydrogens are replaced by these groups, so 4 hydrogens are replaced by these groups, for these groups. Okay, now after the completions of the reactions, what we will do that this is the reaction mixture. After that we will do a workup. Okay, after that what we will do that hydrolysis. Workup means we are doing the hydrolysis, means we will quench it with a acidic medium of water. So now what will happen that we will do that workup, let's say H2O plus. So then what we will do that here what will happen, here we will do that H and here it is going to be OH. Similarly here we will do that H and here going to be OH. So where that this is electronegativity group, so H will go, here comes to that OH and here H and here OH. So likewise how many that will become, this will be this one and this one. So like that for this group that's created. Okay, or I can say that for this group. So now what we will do that after workup you will get this product. So this is the whole mechanisms how this lithium aluminum hydride react with a carbonyl groups. Okay, so what you see here that one LiAlH4, how many carbonyl groups you have needed, that for this type of group has needed. Okay, so it means that whenever we have these groups and we have to take that 4 of these groups and 1 of LiAlH4, and that case we will make that for these groups. Okay, so this is that reactions while you be reacting with the lithium aluminum hydride with any carbonyl groups. Also what we notice here that whenever you are doing, let's say if you that ask the questions that we have that these carbonyl groups and we are giving one each here, one another is we are doing that hydrolysis also. After that we are getting this product. Okay, so whenever you are giving this lithium aluminum hydride and one case, another cases I am taking, let's say isotopes of water I am taking, let's say D3O plus. So from here what you see that this H was always coming from this side, so this will becomes like this, and this H is always comes, this H is always comes from this hydrogen, so here will be that H and here will be O, and that H was coming from this hydrolysis, so here D will come. Okay, similarly if that question is like this, let's say lithium aluminum D4 and let's say this is H3O plus. For this case what will happen that this D is, this H is coming from this, whatever the bond atom will come, that will come from here, so here is D, so here will be the D, and this will be O, and this H is comes from this hydrolysis, so here will be the H. Okay, so this we have to remember while they are doing that problems, wherever they wants to make that sometimes they give lithium aluminum hydride, or sometimes instead of hydrogen they will take any isotopes. On that case we should know that from where which H is coming, this D and the so like such we have did that reactions, we have studied that reactions mechanisms in these groups O and this groups. Okay, so this, let's say this H and let's say this H, and this H comes from this lithium aluminum hydrides, and this comes from hydrolysis, that is H3O plus. Okay, and this H comes from this lithium aluminum hydride. Okay, so this we have to be keep in mind that this H comes from this hydrolysis and this comes from this lithium aluminum hydride that we have seen in these mechanisms also. Okay, so this is the about of this mechanisms, and I already says that this mechanism derived after we doing these experimental results. Okay, so this mechanisms we have to look and has to memorize, and likewise this reactions has happened. Okay, now we will do that where these reactions. So whatever I say that this lithium aluminum hydrides, it is reacted, it is more efficiently used to reduce multiple double bonds, sorry, multiple bonds, sorry, not multiple bonds, polar multiple bonds. It means like these CO groups. Okay, so wherever this type of CO groups, this lithium aluminum hydride is mainly used. Let's say if we have this type of groups, wherever these carbonyl groups are there, like the groups like if there is a aldehydes or this type of carbonyl groups is there, let's say this is a ketones, or this type of carbonyl group is there with, let's say, acid. Okay, and this type of carbonyl groups is there, let's say we have that ester. So in this case, all this case, this lithium aluminum hydride is used to reduce. Okay, or let's say if it is amide groups. So wherever this type of carbonate groups are there, on that case, mainly this lithium aluminum hydride is used to reduce, and it is efficiently it is able to reduce this type of carbonate groups. Okay, so if you take that lithium aluminum hydride and you are taking that hydrolysis, then what we will get? We will get that if it is a aldehyde, then we are getting that 1 degree alcohols. We will get that 1 degree alcohols, and if it is a ketone, then we are getting that 2 degree alcohols, and if it is acid, then again we are getting that 1 degree alcohol. Okay, and if it is acid, then also we are getting the ester, then also we are getting that 1 degree alcohol. And if it is a amide, in this case what we are doing, that 1 degree amine. Okay, so if this carbonyl group, this type of polar multiple bonds are there, then we use this lithium aluminum hydride to reduce to alcohols or to amines. Okay, now let's say for this is the case of this carbonyl groups. Okay, now simply the case is lithium aluminum hydride is used to reduce polar bonds. Polar bonds, like if we say that any groups like this RCH2 X group, and this X groups can be this is X is a leaving groups, can be halogens like iodines and bromines and chlorines. On this case, if you give that lithium aluminum hydrides and we are giving that water hydrolysis, then what happened, that this will be this hydrogens will be attacked to here, and this will reduce, and it convert to RCH3. Okay, so similarly, if this groups is like says this is 1 degree, now it says that R C R H and X is there, this is the 2 degree. On that case also, if you are taking this lithium aluminum hydrides and you are taking that hydrolysis, on this case also you will get that R C H R, and here again we will take the H. But if it is a 3 degree, let's say this is H, and sorry, let's say if it is CH3, and let's say this is also CH3, and this is X. Now we are giving this lithium aluminum hydride and we are doing to that hydrolysis. Then on this case, what happened, that this will attack to this, because this is a what you say that steric hindrance will be there, so this will attack to this, and this will be going to like this, and this is reduced like this. So it will get RCH3, and this is going to be CH2, and this is going to be the CH3. Okay, so this we have to little bit careful, because if there is a steric hindrance will be there, so this H minus will not attack here, H minus will attack to this. Okay, so similarly if you have that R and 3 groups and we are giving that, this is the third case, we are giving that lithium aluminum hydrates and you are doing that hydrolysis. On this case what will happen, that this is converted to RNH2. Okay, and similarly if you have RC triple bond N and you are giving this same things, then on this case what will suit, that this will be going to be reduced RCH2 and NH2. Like if we have take that, if it is that type of bonds, let's say this bonds and here we have that C triple bond N, then also if you are giving this same reagent, then you will get this CH2 and H2. Okay, and also this type of examples also may ask that if that benzene ring is there, here suppose we have the chlorine and we are giving that same this lithium aluminum hydrates and we are giving this hydrolysis, then also we will get that this is will be replaced and you will get that hydrogens. Okay, so either it may be benzene rings or it may be any 5-membered rings. Here we have that H and you are giving the same Cl, also we will get that same things. Okay, so this is the about of this lithium aluminum hydrates, if it is a polar bonds or if it is a non-polar bonds. So what I say here, if that lithium aluminum hydrate, if you are reacting with a polar bonds or polar multiple bonds, then it will do the, it will able to reduce this double bonds, and it also it able to reduce this break this polar bonds. Okay, now the second case is lithium aluminum hydrates is used, which generally not used to reduce non-polar bonds. Okay, like if we have that C triple bond of C, H and H is there and we are giving this lithium aluminum hydrates and we are doing this hydrolysis, then we will get here no reactions. Similarly if we have that C double bond of C and we are giving that same reactions, then also we will get that no reactions. Always that if it is not attached with anything, it's simply the double bonds, triple bonds, then if you are giving this reaction, there will be no reactions. Reason, this is H minus is going, this is a nucleophile. Okay, and this is also electron rich and this is also electron rich, so there will be no reactions between the electron rich and electron rich. Okay, but exception is, exceptional is, let's say we have this double bonds, let's say C double bond of C is there, and or let's say if we have any this type of benzene rings. Okay, here we have this and here we have that COH is there. Now you are giving that lithium aluminum hydrates and you are giving that H3O plus, or I can say that this is at we are giving at, let's say, 35 degrees centigrade, one case, and another case we are giving that lithium aluminum hydrate is getting and we are giving that at 0 degrees centigrade. Okay, another case that we are giving this lithium aluminum hydrates and we are taking in excess. Okay, in this case, and another case is that you are taking this one equivalent of lithium aluminum hydrates. then what will happen? Okay, so for this case, if you are taking in a 35 degree centigrades to this double bond is there, and here conjugation is there with this. Okay, so on that case, at 35 degree centigrade, the double bond also get reduced. Okay, so in this case, what you will see here, this double bond get reduced, and this aldehyde also reduced to alcohols. Okay, and but if you are taking in a 0 degree centigrades, then this double bond is not reduced. On this case, this double bond is remain as it is, only this aldehyde group will get reduced. Okay, but another case, if you are taking excess lithium aluminum hydride, if you are taking in excess amount, on that case also this double bond get reduced. Okay, now if you are taking in a 1 equivalent, on that case also the double bond is not able to reduce. This okay, here CH2 OH. So you understand that if lithium aluminum hydride is excess, or if it is a high temperature, on that case double bond is reduced if it is a conjugations. Okay, if it has to be conjugations. If it is not conjugations, let's say if the CH2 double bond of CH2, here if we are giving that lithium aluminum hydrates 35 degrees centigrade, then also you will get that no reactions. Okay, so if it is a conjugations and that the conditions, it will high temperature, it will, if it is any excess, on that case it is get reduced. Okay, this is the one case. Another, if it is a triple bond. Okay, for triple bonds, for triple bond cases, let's say we have this triple bonds. Okay, on that case, here if you have that this alcohol groups adjacent to this adjacent carbonyls, if you have this alcohol groups, and if you have, let's say, hydrogens, and let's say you have this any groups, 1 2 3 any groups you have. Now we are giving this to this lithium aluminum hydrides. Okay, and we are giving this hydrolysis. On this case, this is get reduced to a trans alkenes, not cis alkene, it get reduced to a cis trans alkene. So this means that this is reduced to a double bonds, and one side, let's say CH2 OH, other side is going to H, and what will happen here, this is going to be the H, and this is going to be 1 2 3 1 2 3. Okay, so this has to be a trans. Okay, so whenever this double bonds is the triple bond is there, and adjacent carbonyl, if alcohol group is there, that is reduced to a trans alkenes. Okay, either alcohol group is there, or it may be that alkene is there. Okay, here H, sorry, here we have that CH2 amines. Okay, either alcohols or amine group is there. Let's say here we have H, let's say we have these groups. Now we are going to give that LiAlH4, and we are giving that water hydrolysis. On this also, this triple bond is get reduced to a double bonds, that is in a trans, not cis. Okay, this is reduced to this bonds, and this is H, let's say here CH2 NH2. Okay, this is same as it is, and this is become a trans. It means that here 1 2 3, here this is going to be a trans. Okay, so always these triple bonds will be reduced to a trans alkenes. Note that into the adjacent carbonyls, either amines is there, or either this alcohol group is there. On that case only this triple bond which get reduced to a double bonds. Okay, and this double bonds can reduce to a single bonds, that is if conjugation is there, and either it is high temperatures or excess amount of lithium aluminum hydride is there, with there has to be a conjugation. On that case it get reduced. Okay, But if simply a double bond or triple bond is there, if you are taking that lithium aluminum hydrates excess or high temperature, then also there will be no reactions. And for alkenes, if you have this alkenes, if you are doing that lithium aluminum hydrates or you are going to do the hydrolysis, then we will get the no reactions. Okay, so these are the basic reactions of lithium aluminum hydrates. In next class we will take more examples with the stereochemistries, and we will discuss about of Cram's models, we will discuss about of Cram's Gillette models, we will discuss about of comfort model. So the details of lithium aluminum hydrate reactions we will discuss with examples in the next class. So today after this, thank you.